முடிச்சோன்னா வாங்கிக்கலாங்க சார். போதும் மிஸ், மைல்டாவே இருந்துட்டு போகுது. போதும் மிஸ், மைல்டாவே இருந்துட்டு போகுது.
அங்க மைக் ஆன்ல இருக்குங்க மீட்டிங். சிஸ்டமோட ஸ்பீக்கர். அங்க மைக் ஆன்ல இருக்குங்க. மைக் ஆமாங்க, மைக் ஆஃப் பண்ணிடுங்க. சரி சார் சார் எம்எல் மேம் இங்கே இருக்க சொன்னாங்க சார் நான் சொல்லிட்டுங்க சார் இந்து இங்கே இருக்க சொன்னாங்க எம்எல் மேம் போன சொல்லுங்க சார் எம்எல் மேம் இங்கே இருக்க சொன்னாங்க சார் நான் சொல்லிட்டுங்க இந்து இங்கே இருக்க சொன்னாங்க எம்எல் மேம் போன சொல்லுங்க சார் எம்எல் மேம் இங்கே இருக்க சொன்னாங்க சார் நான் சொல்லிட்டுங்க இந்து இங்கே இருக்க சொன்னாங்க எம்எல் மேம் போன சொல்லுங்க சார் எம்எல் மேம் இங்கே இருக்க சொன்னாங்க சார் நான் சொல்லிட்டுங்க
சரி, உங்களுக்கு தேர்ட் யூனிட்ல எது முடிச்சிருக்கோம்?
Hello, ma'am. Am I audible?
Pooja, audible? Pooja?
Ma'am, shall we start?
Yeah.
Yes, audible.
Pleasant morning all. It's a great honor to welcome you all to the International One-Week Faculty Development Program and Deep Learning Techniques for Social Media Analytics, jointly organized by Department of Computer Applications, Engineering College, Perry, Tamil Nadu, India, in association with the College of Computing and Information Sciences, University of Technology and Applied Sciences, IPRI, Oman. This program promises to be an enriching experience, bringing together esteemed faculty and researchers from around the globe to delve into the latest advancements in this dynamic field. We extend our warmest greetings to our esteemed resource persons, dedicated organizing team, distinguished faculties and researchers. Welcome, where familiarity meets the undiscovered, and together we create moments that linger in the heart. It's a great pleasure and excitement that we extend a warm welcome to a person who possesses a wealth of knowledge and experience in mathematics, computer science, and engineering. With over 2 decades of dedicated service in academia, she has held positions of increasing responsibility from lecturer to professor at Engineering College, Erode. Her scholarly contributions are vast, encompassing the authorship of 10 books and over 150 papers in esteemed national and international journals. Her contributions extend beyond her scholarly pursuits as she actively engages in professional societies like the Computer Society of India and the Indian Society of Technical Education, fostering knowledge exchange and enhancement. We are privileged to welcome Dr. A. Tamilasi ma'am to deliver the welcome address. Over to you, ma'am.
Okay. Thank you, Pooja. Thank you for the brief introduction about myself. Warm good morning to one and all present in the online platform. First and foremost, I welcome the August gathering for the collaborative international one-week starting from today, FDP by Engineering College, Tamil Nadu, India, and College of Computing and Information Sciences, University of Technology and Applied Sciences, Oman, to exchange a research idea and innovation on the title Deep Learning Techniques for social media analysis, which is a trend restriction of data. Well, of technology and applied sciences women. Next, I would like to welcome the organizers of both hosting teams, Professor Amal Vate, Sayed, HOD of IT, Dr. Hemlata, and Dr. Wilfred Blessing from University of Technology and Applied Sciences women, and our organizers, Dr. M. Paigodi and Dr. Vijay Kumar, who made lot of effort for organizing this program. Also, I'm very much happy to welcome the participants from various colleges. And also, I would like to welcome the resource persons from the Department of Computer Science and Engineering, Computer Science and Design, Engineering College, and Dr. Professor Mankesh, Department of IT. Here, I would like to tell something about our research persons. They are very dynamic researchers, and they are going to discuss about applications of DL to social media data. Here we take social media data like Twitter, Facebook, so on. They are going to give the applications of deep learning in social media data. I think this 5-day program will give you insight about. Once again, I welcome all. I hand over the session to Professor Rangarajan, sir. Thank you all.
Thank you, madam.
Thank you,
sir.
for giving a warm welcome. It's a great pleasure to extend a warm welcome to a person whose remarkable achievements and contributions in the field of software engineering, personalized e-learning, and social collaboration. Her professional journey as head of information technology departments and as lecturer at esteemed institutions such as University of Technology and Applied Sciences, College of Technology, and Sultan Qaboos University, underscores their leadership and dedication to academic excellence. Now let's welcome Dr. Amal Bhattacharya ma'am, HOD IT, College of Computing and Information Sciences, to deliver the inaugural address.
Thank you so much. Thank you so much for that. I'm audible to everyone?
Yes, ma'am.
Okay, thank you so much.
Good morning.
Good morning, everyone, and greetings to you all, and welcome to this program on deep learning techniques for social media analytics. Of course, the rise of social media platforms actually lead us in order to overwhelming this amount of data generated using these platforms in order to think about how we can really utilize this information in a better way for the usefulness of researchers and educators. During this faculty development program, we are going to delve deeply actually into the deep learning techniques in social media analytics, and also we are going to utilize experts who are really the resource persons who are really well equipped with knowledge and experts in the field of deep learning techniques in social media analytics. We will explore various methodologies, algorithms, and tools that can be employed to extract the meaningful information from social media platforms. As educators, understanding these techniques is very vital and very important in order to keep up with the rapid advancement technologies, and also in order to equip our students with the necessary skills and knowledge in this digital age. Now, these faculty programs also will enable to contribute to the research community by exploring novel approaches and methodologies for deep learning in social media analysis. By collaborating and sharing our experiences, we can derive innovation in this exciting field and also to make significant contribution to the academic and the practical applications of deep learning in social media analytics. Let us seize this opportunity in order to enhance our understanding and in deep learning techniques for social media, and together unlock the transformative potential that lie within the world of social media data. Finally, I would like really to express my heartfelt gratitude to Congo Engineering College, India, for collaborating with University of Technology and Applied Science, Oman, Abri, in organizing these enlightening sessions. Thank you so much. And welcome you all. And please take the opportunity of this program in order really to acquire the knowledge and the practical experiences in this field. Thank you so much, and welcome you all.
Thank you, ma'am, for your warm address. It's my distinct pleasure to extend a warm and cordial welcome to a person who has illustrious career and extensive contributions to the field of theoretical computer science, artificial intelligence, natural language processing, and machine learning. With over 27 years of teaching experience, his expertise and research have significantly enriched the academic community. His impressive publication record, compressing numerous papers in prestigious international journals and presentations at esteemed conferences, reflects a deep commitment to advanced knowledge in cutting-edge technologies. Moreover, your innovative approach to teaching and learning, evidenced by the development of video materials and post materials for BTech courses, underscores your dedication to fostering a transformative education experience for your students. He was awarded the best single point of contact award from Infosys in 2006. Furthermore, he was being honored with Best Faculty Award for academic years 2017 to 18 and CPS Best Faculty Award for the year 2018 to 19 by Congo College. Now it's time to welcome Dr. R. Nagarajan sir, Professor, Department of Computer System and Design, Congo Engineering College, to take over the session on role of deep learning techniques in social media data analytics. Over to you, sir.
Thank you so much. I hope everyone can hear me.
Yes, thank you.
Okay. Yeah. So I can start my presentation. At the outset, let me thank the organizers, the Congo Engineering College and University of Technology, Oman, for having given me an opportunity to interact with the teaching fraternity. So as an initial, the first lecture on this FDP. So I would like to talk to you about, discuss with you about social network analysis and how deep learning can be applied in social network analysis. So please wait so that I can share my PowerPoint. Okay. Is my screen visible?
Yes.
Yeah. Okay. Thank you so much, sir. Yes, once again, welcome you to this topic. Social network analysis and deep learning is what I'm going to discuss for the next 1 hour. So as introduced by the comparing team, actually, I'm working as professor in the Department of Computer Science and Engineering, Information Technology at Congo Engineering College since to 1995. Okay. So my present area of interest. Okay. I deal with algorithms, theoretical computer science, and artificial intelligence and machine learning. So today, presently, I am working with research scholars who are working in diverse fields like application of deep learning techniques to various problems in medical sciences, social network analysis, and other areas. Okay. So let me take you to what is actually meant by network analysis. Okay. So we are daily we are using our social networks. Okay. So let it be WhatsApp or Twitter, okay, or Facebook. Okay. So and this is not new recently. Actually, even in olden days, there is network. Okay. So you can just very well see on the figure here that this shows. Yeah. So you can see here that you can see here that this is a network. Okay, network of streets. All the streets are connected. Okay. And this you can see is a very old network of Königsberg Bridge. Okay, so which is attributed to this Euler circuit. Okay, so this was there were two islands. Okay, so in this bridge. So one island is here. This is one island, and this is the second island. And these islands are connected by to the main line by seven bridges. Okay, so you can see there are seven bridges that are connecting the two islands, to the main line. One, two, three, four, five, six, seven. And this river is called the Prague River, and this city is called Königsberg. Okay. So actually, this the problem here was actually which actually motivated Euler to invent the graph theory. So graph theory was becoming a formal subject after this problem. So what actually this Euler he postulated, or sorry, he put forward formulated that you have to cross the bridge exactly once. Okay, and you have to cover all the seven bridges. Okay. So you have to bring you have to have a Euler path so that you can start from any place, but you have to cross the bridges exactly once. You should not cross any bridge twice. Okay. And you have to come back to the sorry, need not come back to the starting place. So that's not necessary. Say, for example, if I start here, so I can go here, I can come here, then I can go here like this. I can do, but I have to cross the bridges exactly one. Any bridge you take, I have to cross exactly one. Okay. And it was found that this particular what do you call this topology, what you see here, can be represented as a graph. Okay, so you can see this. There are four nodes. So this is node 1, this is node 2, this is node 3, and this is node 4. Okay, node 4. And you can see that how they are connected. Okay, so node 1 is connected to node 2, node 3. Okay, so here I will just rewrite it. So this is node 1, this is 2, this is 3, and this is 4. So this is connected by two bridges. This is connected by two bridges. This is one bridge, and this is one bridge that connects node 3 and 4. That is, the two islands are connected by a bridge. Okay. And now you can start from any vertex. Okay. And you can traverse the edges of this graph. And your job is to traverse exactly once every edge. Okay. And see that whether you can cover all the edges. So it was found that you cannot do that. Okay. So that was the problem. So this actually this problem was actually the one that is actually motivated Euler to create a new field of mathematics that's called graph theory. Okay, so that's how it started. And so in olden days, you can say that you can take any network. So network doesn't represent the modern computer networks. Okay, so let it be a trade. Okay, so in those days there was trade. So there used to be trades. Okay, so there was a hub. Okay, and you have a network. Okay, you take the railways. So railways is a network. Okay. You you take the highways in a state, in a city, you can take the highways. So in the highways, you can find that these are the intersections of the roads. The intersection of the roads, they become the nodes, and the roads themselves become the edges. Okay, so like that. So any network, okay, can be transformed into a graph. Okay, and the beautiful thing about graph is that there is a rich set of literature that's available on analysis of graphs. Okay, and we can have a lot of problems that can be solved using graphs. Okay, so that's what actually it started all with. And now you know that when, in the present scenario, when you have a lot of social networks, for example, you take the example of Twitter, or you take the example of Facebook, or you take the example of, say, Instagram. Okay, so how does how do we analyze that? Because these networks are not simple; they are complex. They are very large networks. Okay, and how do we analyze that using graph theoretic approaches? Okay, so that is what is called social network analysis. And you can find that there are different types of networks. Like, for example, you take the example of Facebook. Facebook is a graph where, say, for example, I am a friend of somebody A, and some person A by name A is a friend of B. So that means that B is a friend of A. So it means that they are both of them are connected by an edge. Okay, which is undirected edge. Okay, so it is an undirected graph. When you take a Facebook, it's an undirected graph. On the other hand, if you take a Twitter or you take Instagram, so these are not undirected, because in Twitter or Instagram, we follow. Like, for example, A follows B. Okay. But B need not follow A. It's not necessary that B follows A. A follows B, but B doesn't follow A. So there's an edge, directed edge from A to B and not from B to A. Okay. So such networks are called directed networks. Okay. So undirected and directed networks, undirected and directed graphs, they represent different networks. So likewise, so that's what we are going to see today, that how this uh, graph theoretic approach can be applied, okay, to this large networks in real time. Okay, so that's what you will see. So just I will not go through every point. Okay, so just you can see here. Okay, so you can see that here you can see that there is a uh, you can just see here. Okay, so you have two large networks. Actually, it's the visualization of US bloggers shows clearly how they tend to link predominantly to blogs supporting the same party. So as you know that in US, actually there are two parties: the Democratic Party and the Presidential Party. And so here, so this the blue nodes, they represent one party, and the red ones the other party. Okay. And you can see when you visualize them, okay, so you can see that how they communicate, okay, how they communicate. So how the people, they are connected. So you can see a large network here. Okay. So the single network. So you can see two different communities. You can see a community here. Okay. So two different communities and how they interact between the communities. Okay. So clearly shows you that there are two clusters. Okay, and this study was done in 2005. Okay, so you can just see. Okay, and if you take other examples, maybe you take a simple graph like this. Okay, so simple graph. Okay, so you can just you see how this graph and this graph are different. Okay, and there are other domains where we can apply social network analysis. For example, this is a network. This network is called the internet. Okay, so this is the internet network. So generally, our World Wide Web. World Wide Web. Okay, so this is an interesting network. Okay, so you can see that this is the central network, and you can see here that this is the people who are actually directed towards the central network. Okay, and this is the people who are directed out of the central network. Okay, so this network shows a example of a bow tie. Okay, so you can see it's a bow tie. Okay, so that you have a middle part and you have an in part and an out part. Okay, so this kind of a graph. Okay, so this actually helps you. Okay, so you can see in this example, I collected a large amount of data on the links between web pages. So this graph shows links between web pages, and okay, so you can see most other web pages either link to or linked to from that core. So you can see here a core. Okay, core of pages in the middle. Okay, so there are so many other pages which are linked inside to this, and this core actually links out to these other pages. Okay, so you so you can just see how the structure of this network looks like. Okay, when you visualize. Okay, so practical applications you can have any number. Okay, you can just for that matter. You can apply social network analysis to large uh, different networks, as I already said. Okay. Yeah. So the basic concepts, actually we are going to see. Say, so how to represent a network. Okay. What do you mean by ties? Okay. So how the networks are linked, nodes are linked, and key players. Okay. How do you identify nodes which are prominent? Okay. And then you can see how the entire network as a network, the complete network, the overall network is stable or not. Okay, whether that a network may, whether you call the network is resilient. Okay, network resilience. Okay, when you delete a node, what happens when you delete a node, or what happens when you delete an edge? So does the network fall apart? Okay, so that is the fourth one, the cohesion. Okay, that tells you about the resilience of a network. Okay, so this is what we are going to see. Say, for example, this is a very simple edge. So this is a simple graph. Okay. So you can see there are four nodes. Okay. Say node one, node two, node three, node four, and each node is called a vertex. And the vertex, they are connected. Okay. Say, for example, one and two are connected, one and three are connected. Okay. Right. So you can see like that. Okay. So this shows you how the networks are connected and how they are in okay. So a graph, so it's a directed graph. As I already told you, there's an edge which is directed. Okay, so one is directed to three. Okay, pointing to three, but three doesn't point to one. So it's like one follows three, and three doesn't follow one, something like that. Okay. And every network, okay, so every network can be, or a graph can be represented as an adjacency matrix. So you can see that's an adjacency matrix here. So you have vertex, four vertex, and if there is a link between the vertex, we call it, you make it one. For example, there's a link between one and two. So we have a one here, and there's no link between loop. There's no loop between one to one. There's no loop. So that is not there. So you can say that it is the one to one, two to two. So the diagonal part is empty, but the other part, if there is a link, it is one. Otherwise, if there's no link, it is zero. Okay. So this is called adjacency matrix, and sometimes we have a weight matrix also. Like for example, if this particular graph if has a strength of 4, so instead of calling it a 1, I can call it 4. Here I can put the weight as 4. Okay, and suppose the weight between 3 and 4, 4 and 3 is say 2. So 4 and 3. So instead of saying 1 means that's an edge. Or I can represent, if it's a weighted graph, I can simply put the weight here. Okay. So this is an adjacency matrix or a weighted matrix. Okay. And an efficient way of representing a sparse graph. For example, adjacency matrix takes up a lot of space. Okay. But whereas if your graph has a lot of nodes, but the edges are very sparse, in that case, I can always go for a edge list. Like for example, like showing here, I can see that how the edge list. Say, for example, vertex one is connected to vertex one is connected to three. Okay, there's an edge between vertex one and three. There's an edge between vertex one and two. Okay, you can see these two. So this is this edge and this edge. Similarly, there's an edge between 2 and 3. There's an edge between 2 and 3. So this is an edge between 2 and 3. So likewise, so this you can take this example and you can show that how you can represent a graph. Okay. So now, so as I already told you, this is a directed graph where there is edge between two nodes if they are related by some directed edges, or an undirected graph where both of them are related. For example, in a Facebook, I can say 1 and 3 are friends. So that's a undirected edge between 1 and 3. Okay. So in that case, your adjacency matrix will be a symmetric matrix. So as shown here, it becomes symmetric. Okay. Now there are things that we need to come across. For example, what is called ego network. For example, if you take node 3 here. Okay. So the network that comprises nodes that are connected to only node 3. Okay. So which includes, say, node 4, node 1, node 2, and node 5. Okay. And so this is a network. So if you take this one, this edge, this edge, this edge, okay, and this edge, okay. So 5 is also included. So this edge and this edge. So you can find this. So this is an ego network. Call it an ego network. So that is centered around 3. Okay, for 3. For 3 it is centered. Okay. So this is so when you remove that, so what happens is that when you remove node 3, so you can see that the 4 becomes isolated. Okay, so 4, this edge goes away, so 4 becomes isolated. Okay. So you can see why it's called an ego network, because it tells you how they are connected. Okay, so how many nodes are neighbors of 3? Okay, so like that. So this is called. Next comes time strength. Okay, say for example, how your edges are connected. Okay, how the edges are connected. For example, if you take this, okay, as I told you already, so I already told you that you can have a wedge, but at the same time, you can also have some weights associated with the edges. Okay. So this edge has a weight of 30. Okay. So it gives you the strength of that particular edge. Okay. So this is a weighted graph. So actually, what does it tell you? The edge weights represent strength of the relationship between A and B. For example, you have a node A and a node B. So how they are connected and what is the strength of that connection? Maybe you can take it, the edge can be a cost. For example, say for example, A is a city, B is a city. Then there's a road link that connects between A and B. And this thing, you can call it as the distance. You can call it as the distance between A and B. Or cost of traveling from A to B. Okay. So that can be represented as a weight on the edge. So I can put a weight here. Okay. So next is homophily, some terms that you need to know. That is homophily, transitivity, and bridging. Okay, so this concept you need to know. So before I go to that, so I'll tell you that there's a thing that actually you need to know about the ties. Okay, so that's a very good experiment that was done long back. So where they can say that, for example, you have a friends network, say for example, as they're shown here. So this 1, 2, 3, 4, they are all connected, well connected. Okay. And you may represent them as a friend. Okay. Say that when you take 2, 1, 3, 4, they are strongly connected with. Okay. But you may have another graph here. Say, for example, you may have a graph node 4, 5, and 6. So in which say 4 may be connected to 2. Okay. So this is a weak link. So this is called a weak link. But whereas these are strong things because they form a cluster, a group. Okay. And this actually may be your distant friend. For example, these may be the current employees. 1, 3, 4, they may be the current employees. But whereas 4 may be maybe a classmate of 2 when they were in college or school. Okay. So it's a weak tie. Okay. So there was a very good experiment that was done with weak and strong ties. That they say that generally the weak ties is one that gives you more advantage. Okay, for example, say for example, this 2 is applying for a new job. Okay, for 2 is applying for a new job. In that case, 1, 3, and 4 may not be for so help, whereas a weak tie with 4 may help 2 to get a new job. Okay. So that was the thing that actually was found out in the using this relationship. Now coming to edge weights, okay, so this already we discussed. Yeah, now we have three more topics that we need to discuss. This what is homophily. Okay, say for example, homophily tends to relate people with similar characteristics. Like for example, uh, those people who are have the same interest. Okay, so that you can see as a cluster in a graph. Okay, that you can always find out as cluster in a graph. Uh, so as I already mentioned, there can be a strong connection or a weak connection. Transitivity is actually, for example, if A and B are connected and B and C are connected, then A and C may become connected very soon. For example, A is there, B is there, C is there. A and B are connected, B and C are connected. Okay. So there is chance that because of this middle B, that A and C may become introduced to each other, and finally a link may also come here. This dotted line may be a link that may develop in future. Okay, so this is called transitivity. Okay. Next is bridges. So bridges are actually very good examples. For example, as I already gave an example there. So you may have a graph like this, where there's a strong connection between these nodes. There's a strong connection between these nodes, but there's a connection between this and this. So this connection is called a bridge. Okay. So because when you remove this edge, what happens is you get two disjoint sets. You get two disjoint sets or two disjoint graphs. Okay. So, but when this bridge, when this edge is present, it actually links between two clusters. Okay. So bridges are very important in our because they facilitate inter-group communication. Okay. Right. And they also spur innovation. Actually, when you talk about, say, researchers, so you have a group of researchers working here, group of researchers working there on different topics, A and B, say, for example, on topic A and B. A bridge may help you to form a intercluster or may form you an interdisciplinary research between group A and B. Okay. So that's why bridges are very. Next comes how to identify central key nodes in a network. Say, for example, I have a network. Say, for example, I may have network. So, is all the nodes, or whether there are any key players in this node? Okay, so I want, for example, like this. So, like for example, I may have a network like this. Okay. Say in this case, you can find that. So you can see that this node is actually having a lot of associations with other nodes. Okay. So you can have a graph like this. So in that case, you can find that this node is a little prominent. How? Because it depends upon the number of edges that are incident. So here in this case, how many edges? 1, 2, 3, 4, 5, 6 edges. So 6 edges. So there's a degree. You know what's the thing? What do you mean by degree of a node? Degree of a node represents the number of edges that are incident on that present node. Okay. So this degree means that this particular node is connected to all other nodes in the graph. So this may be a key player. Okay. So that's what we are going to see. Okay. So a simple example I have just taken. But there are other key players also that we will see in this thing. Okay. For example, this is called degree centrality, as I already mentioned, degree centrality. So centrality is the measure of measuring the key positions. Okay. So prominence of a node. Okay. In a graph. Okay. So here you can see that degree centrality is, for example, so how many degrees of node 3? 4. 4 is the degree of node 3. And 3 is the degree of node 2. Okay. 2 is the degree of node 1. Okay. Similarly, here you can see that node 5 has a degree 4. Okay. But whereas node 4, if you take, it has only 1 degree 1. Okay. So in this case, so you can just find out that suppose if it is a directed graph, then we also need to take into account whether it's an in degree or out degree. Okay. Say here in this case it's under graph, so we simply take the example of degree. Okay. So we don't have an in degree or out degree. Okay. So here you can see that from this you can find that nodes 3 and node 5. Okay, these two nodes, they form a kind of prominence. Okay. So when you remove them, you can see what actually remains after that is the network. This is what actually remains. If you remove that, okay, so these two will form one network, and these nodes become disjoint. They become disconnected. Okay, so that's called prominence. Okay, so it measures connectedness. Okay, say for example, this is very useful. Okay, in case of a campaigning, election campaigning, or maybe say injecting a new fashion. Okay. So you can see that graph theory is actually applicable in a lot of areas. Okay. Not just social networks, it can be applied to biological networks also. For example, say you want to have a medicine. When you inject the medicine in node 3, it reaches the other parts very fast. Okay. So in that case, so the nodes connectedness to the graph is measured as a degree. Okay. So this is very important. It's one of the measures that measure the centrality. And the other things are what is a path and what is the shortest path. So these things I need not spend much time. Okay. Say, for example, I want to reach from node, say, I want to reach from node, say, 3 to 2. So in that case, I can reach through to several. So I can come here and go this way, or I can come this way or this way. So these are paths. Okay. So these are paths. And the shortest path is one that has the least number of edges between two nodes. Okay. Or if the nodes are numbered, if the nodes are weighted, for example, this weight is 3, 5, 3, 2. Okay. In that case, say this weight is 30 between 3 and 2. So the shortest path will be from 5 to 2. Okay. So the shortest path will be from 3 to 1 and 1 to 2, rather than going directly from 3 to 1, 2. Okay. So this is expensive. But whereas if you go through node 1, it is shortest. Okay. So maybe meaning in so here so it depends upon how you make the things shortest, or how you apply weights. That determines the smallest weight of edges in the sequence. That sequence of edges is called a path, and the sum of all the weights of the edges, and the smallest one is called the shortest one. Okay, so like you can have a shortest path. Now I come to the another type of centrality, that is called the betweenness centrality. So we have already seen degree centrality. Now this is the betweenness centrality. Here you can find that there is something called, say, for example, if you take node 3, it is having it is between two pairs. Say, for example, this is one network and this is another. So you can see that this, suppose if 3, 2, and 5, they want to communicate to 4, they cannot communicate directly. They have to communicate only through 3. So 3 is between. Okay. Say, for example, I can have some better illustration here. Even though, for example, you may have a node here also. Okay. Even though the degree of this node here is small, it is only 2. Okay. This is one edge and this other edge. So the degree is 2. But this is an important node because it is between two groups. You can see one group is here and another group is here. And this is the only thing that is connecting. This node is the only group that is only node that's connecting these two groups. Okay. So therefore, it has a very high betweenness centrality. Okay. And this betweenness centrality, helps to identify a prominence. So you can now just see that prominence is not in terms of number of degrees you have. Prominence can be where you are actually placed in the network. For example, in this network, the degree is small, but still the position of this node in this network is such a way that it actually it forms a what you call a link between two different subgroups. Okay, so in that case, anybody from this group wants to communicate to this group, they have to go through this node. Okay, so this actually forms something like a broker. Okay, so it's holding a prominent place. Okay, so that is called between a central. Okay. Closeness centrality. Closeness centrality is how close a node is there so as to reach the rest of the network. Okay, how close is the node? So it means calculate the mean length of all shortest path from the node to all other nodes in the network. And you can see, you can take the average of it, that gives you the closeness centrality. Say how close is 3? How close is 3 to all other nodes in the graph? Okay. So you have to find the shortest path from 3 to 1, shortest path from 3 to 2, shortest path from 3 to 4, shortest path from 3 to 7. So likewise, you have to find the shortest path and then divide by the number of paths. Then you get a value. So here you can see that this closeness centrality of 3 is very high, which means that this 3 and 5, they are the people, not just they have the highest number of degree, but they are also very close to the rest of the network. Okay. So, example 3, if you send an information to 3, that information can be transmitted to 1, 2, 4, and 5 very fast, or maybe 6 and 7 also. Yeah. But if you take the node, say for example 4 or 6, their closeness is very limited. Okay, so they are not close because you take from 4, say you want to reach, say from 4 you want to reach 7. So then you have to go like this. So you have to go like this you have to go. Or from 4, I want to reach 2, I have to go like this. Okay. So likewise, so this 4 has a very small, what do you call, closeness interval. Okay. So this is actually what is meant by closeness interval. That is, it's a measure of reaching. It's a measure of reaching the rest of the network. Okay. So this is again another thing that you have to think about. Okay. Now, just give me a minute off so that I can now just change my batteries. Yeah, can you hear me? Anybody can just give a feedback. Hello.
Yes, sir, hearing.
You can hear me now?
We can hear you.
Yeah. Okay. So there was a problem with my wireless mic. So actually, I have to. Okay, no problem. Okay. Okay. So just as I was mentioning, now I come to another. I can come to another next topic, that is the eigenvector centrality. So this is a centrality that is closely related to page rank. Okay, that was used in Google. Google search engine. So this actually measures the prominence not based on degree or the position or the closeness, but it measures the centrality of a node with respect to the other nodes. For example, if you take the centrality, maybe for example, you have say you have a person, a node is there. Say maybe you take a citation network. Okay, so this is a paper. Okay, a paper called A, and this paper is being referred by this another paper called B. Okay, they are manuscripts, papers, research papers, which A actually refers, sorry, B refers A. Okay, but there are so many other papers that refer B. There are so many other papers which refer B. So in this case, you can find that B is a paper that is being referred by so many other people. Okay, so naturally it's going to have a higher centrality. Okay, but even though A doesn't have much of the citations, but actually B refers to A. Okay, so in that case, since the centrality of B is very high, also that makes A's centrality much bigger than B. So are you getting the point? So it's like, for example, popularity. Okay, say for example, so A, I can say that it's popular, more popular than B, because even though A has a very smaller number of edges, that is only B is actually referring to A. But since B already is actually a popular paper, so A has to be a more popular paper. Okay, so this is called the eigenvector centrality. So this is how the page rank works. Okay, in our Google algorithm, the page rank works in this manner. Okay, so it measures. So here you can see that a node. So you can just see here that a node with a high eigenvector centrality is connected to other nodes with high eigenvector centrality. Okay, so this is how as I already mentioned, the Google ranks web pages. Okay, right. So you can see that centrality measures what you have seen. So degree, betweenness, and closeness, and eigenvector. So these are different types of centrality measures that are very useful in our things. Okay, in our analysis of social networks. Now, generally, you can see that this in this figure. So they accordingly, you can see that they have based on the size, they have made it. For example, you can see that node 10 has a bigger size. 3 and 5 have the same size. Okay, and rest of the nodes have the same size. So you can see that different colors are used, different sizes are used, or so that tells you about the centrality. Now, looking at this graph, visualizing this graph, you can say that this node 10, node 3, and node 5, they are the key players. Okay, either as you can find that the 3 and 5. Okay, so you can find that this is one group, and this is another group. Okay, and it is the 3 and 5 that form the bridge between these two groups. Okay, and so depending upon the different kinds of centrality, you can assign different colors, you can assign different sizes to the nodes to identify key players. So cohesion, I told you that is how resilient a network is. Okay. Say, for example, the ratio of the number of relations which are reciprocated, there is a edge in both directions over the total number of relations in the network. Okay. The two vertices are said to be related if they are at least one edge between them. Okay. So, like for example, you can see that here you can see a directed graph. You can see that uh, these are related if you have at least one edge. Okay. Reciprocity means reciprocity means in the example you can see there that whether it is considered. So, for example, you can see that so there are how many edges are there? 1, 2, 3, 4, 5, 6, 7. Say, for example, if you take so reciprocity means, say, for example, if node 1 is connected to node 3, then there should be a connection from node 3 to node 1. Okay, so in this case, you can find there's a reciprocity between 1 and 3. Similarly, there's a reciprocity between 2 and 3. Okay, so there is a link. But whereas between 1 and 2, there's no reciprocity. There's one is connected to 2 and the other way is not connected. Okay, so right. And density refers to the number of edges that are present. Okay, for example, if you take a graph, in this graph, if you take this graph has 4 nodes and maximum number of edges you can have is 1, 2, 3. So you can have 1, 2, 3, 4, 5, 6. You can have 6 edges maximum. So that 6 edges will connect almost all the, for example, from 1, I'm connected to all the 3 nodes. From 1, I'm connected to all the 3 nodes. Similarly, from 2 also, I'm connected to all the remaining nodes. So there's an edge between, so there's an edge between that. Okay, so that number of edges. Okay, so how many number of edges are there? So it is actually n into n minus 1 by 2. Okay, the maximum number of edges you can have. Okay, if it is a directed graph, then you have to have multiply by 2. Okay, so in that case, you can find that this, for example, if I have a graph like this, say, I'll take the example of a undirected graph. Say you can take this graph. So say, for example, how many edges are there? So actually 1, 2, 3, 4, 5. So there are 5 edges, but maximum how many edges can be there? 6. So the density of this graph is 5 by 6. Okay. So the density of this graph is 5 by 6. Okay. So as I told you that there can be n into n minus 1 by 2. That is the maximum number of edges you can have. Okay. In any graph where n is the number of nodes. Okay. So in that case, the 5 by 6 in this graph. So as I told you here, the 5 by 6 is the number of called the density of the graph. So the density of the graph tells you how sparsely or how densely the nodes in a graph are connected. Okay, so that gives you an idea about that. Yeah, this is again another very important topic, that is clustering. Okay, so this is a very important topic when it comes to analysis of social networks. So it says so the clustering coefficient is how within a network, okay, whether the nodes are connected uniformly or do you find clusters. For example, this is a network. In this network, there may be some set of nodes which are densely connected. And there may be sparse links between them. Okay. So like, for example, some set of nodes are densely connected. Okay. So each, what I call it a cluster. Okay. Because nodes within the cluster, they are densely connected. Okay. But between inter-cluster, I have a small connection, which I call the big tag, as I said before. Okay. So here in this example, you can take that this forms one cluster. Okay. And this forms another cluster. Okay. So so to finding a cluster in a given network is a NP hard problem. So already you know that. Okay. So it is a hard problem. Okay. So we cannot. So we have to go for a unsupervised learning through, and we have to assume. Okay, or we have to guess the number of clusters beforehand. Okay. So because there's always, or you can very well say that this entire graph is a single cluster. I can say that. Okay, there's nothing wrong in doing that. Okay, I can say that entire graph is a single cluster. Or if the number of clusters is 2, I can say that 5, 6, 7 form one cluster, 1, 2, 3, and 4 form another cluster. I can come to terms like that. Okay, but you can see that this is what actually the thing is. Okay, so clustering is a very, very important thing. So clustering is very much applicable in lot of areas. Okay, so that we'll see as I come. Okay. So now, what is the diameter of the network? Okay, so it is the diameter is the average longest distance. Okay, or I will say the shortest longest distance. Okay, so for example, you have two nodes. Okay, for example, node and node 7. Okay, so they are, what is the shortest path between them? The shortest path between them is 3. Okay, so this is called the shortest longest distance, and that is called the diameter, okay, of the network. So this is again another thing that actually very important in case of networks. Yeah. Then another thing that you need to know is about the small world problem. So this small world problem says that whatever be the size of the network, okay, you can just take the size of the network. Any two nodes, if you take, for example, this is a network, I have two, you can take any two nodes. And if I want to find what is the shortest distance between them, so it will be around 6, not more than that. Okay, it's maybe around 6. So that's what they say, 6 degrees of separation. Okay. For example, if you know that, for example, myself, if you take myself and if you take anybody whom you know, for example, don't know directly. Okay. For example, the president of United States, you can take something like that. Okay. Say this is you and this is president of US. Now, we do not know, you do not know him, don't know him directly. Okay. But if you just take your through your acquaintances. For example, acquaintances from your friends. Okay, you have friends that is around you, and those friends may have other friends around them. So like that, if you take single hops in that way, then the maximum distance between you and the president of US, even though you do not know each other closely, the maximum distance will not be more than 6. That's what actually that they say that it is a small world problem. So this was the problem that was experimented long back in social network analysis, and they found that the maximum number of edges will be 6. So next one is preferential attachment or the rich get richer phenomenon. This is rich get richer phenomenon. So here you can find that, say, for example, if you take a big network like this, you can see a big network like this. So you can find that, say, for example, you take this node here and a node that is here. Okay. So this node has a very small degree, but whereas this node has a very high degree. Okay. So when a new node comes, most probably where is going to attach? This node is going to be attached here. Okay. So that's called preferential attachment, or it's called the scale-free network. So that means rich get richer phenomenon. So that's like, for example, if you take a population of, say, India, say it is around 130 crores, then how many are rich? How many percentage of people are really rich? Rich means, so that is countable, is it not so? So you can have not more than 50. Okay, so who are millionaires? If you count billionaires in a population of 130 crores, so the maximum number of billionaires will be countable. It will be not more than 50. Okay, so that's the reason you can see that the scale-free network has a structure like this. So it has a structure like this. So most of the population will have very small degree, and a very small portion of the population have very large degree. So the graph will be exponential graph. Okay. And a new node that comes in may most probably get attached to a node that is already having higher number of degree. Okay. Or higher number of centrality. Okay. So that's called preferential attachment. Okay, so just I will not go much through this. Now I'll come to another part of my lecture, that is the deep learning and how you really go about using deep learning in your networks. Okay, so I will just change my yeah. Okay, so I'll just continue for another 10 minutes, and then we can close. So this part of the lecture is actually based on the deep learning approach. Okay, so how deep learning has enabled uh, uh, learning in graphs much easier. Okay, so you can see that. So here, this graph tells you about the different kinds of what is the path research, how it led from 1958 to the present 2018. Okay, so you have now it's 2020. Sorry, up to 20, and because we are already in 2024. Okay, so you can see that the research in AI started long back, 1958. Okay, so it was the first time when Rosenblatt he proposed the perceptron. Okay, and then the Hubble and Wiesel, they are the people who are working with the human cortex, visual cortex. They were able to tell you how this image processing is actually carried out in the brain. That is 1959, and you can see that the back propagation algorithm was invented somewhere in 1982. Okay, then something called the first neurocognitron came up here, 1987. And 1995, actually, your support vector machine came, the machine learning technique support vector machine came in this region. And, so after the advent of the first GPU, okay, so the graphical processing unit, or what you call the SIMD, okay, so single instruction, multiple data, vector processing. After that became that is only after getting the support of the first GPU, that again this thing actually came into what you call being adopted. Otherwise, you know that AI had a lot of winters. What do you call it? Winter means people lose interest in pursuing research in AI. And AI and neural networks, they have faced a lot of winters. When I say winter means nobody will pursue research in that area. But why the winters came? The winters came because of the inability to implement, because the lack of technology to support the research. Okay. But after the advent of GPU, and after our web services, different cloud computing technologies came, after getting the support of cloud computing technologies like Amazon or Google, Microsoft, okay? And after that, you can see that these algorithms, again, the same backpropagation algorithms, they could overcome the problem of vanishing and exploding gradients in backpropagation learning, that led to the advent of deep neural networks. Okay, so deep neural networks came only after this thing. And similarly, there was a lot of data sets that were actually being invented. That you can see the ImageNet around 2010. Okay, and these are called the what do you call the what do you call the motivation that actually let people come up. Okay, so like the TensorFlow, okay, libraries. Okay, now you can see that in 2018, and now today we are now somewhere after 2020 or 24, we are now somewhere that we are able to use. We are now presently we are now in a very what do you call so here you can see, okay, the deep learning came after 2012. Okay, now you can see that the error rate has minimized. Okay, so to a quite small, because of the advent of technology. Okay, now here you can see that, and now we are talking about natural language understanding fueled by transformers. Now we have the transformer architecture. Okay, the transformer architectures are the encoder decoder architectures. Okay, so like the encoders, like the BERT, okay, and the decoders, okay, like your generative AI, okay, like your chat GPT, okay. So these have actually revolutionized the use of, that is the research in natural language processing mostly, and we call them the transformer models. Okay, like for example, in those days, when you are given an image, you need to have a lot of work to be done to identify features. For example, this, when you take this image, there are so many features. Like for example, there are 4 wheels, there's a windshield, there are 2 headlights. Based on that, your classifier has to say it's a car. But nowadays, just you have a deep network which is available that can automatically extract the features and identify the car directly from the image. Okay, but there's still a problem is actually, so when you are given a raw data, you should have a structured, you have to convert it into a structured data, then you have to do feature engineering, then give a learning algorithm and a model. So the first pain, okay, is data scientists have to hand encode features. So that's the first pain. The second pain is the data is often incomplete. Okay, for example, if you take information about say proteins and other things, so there's a lot of things that is actually missing. Okay. So in that case, so now what actually we have, what is the present day we do is actually we do processing with images and text. So images are grid. Actually, they are form of a grid. You can have a length and breadth. Yes. Hello. Hello. Can you hear me? Hello. Hello. Can you hear me?
Yes, sir. Yes, sir.
Yes, sir.
So I think there was some disturbance, okay.
So,
Okay, no
wait a
problem.
few minutes, sir. Hello. நான் கேட்கறது பேச மாட்டேங்குதே.
I think some mic is on, and so okay, yeah, and I will just continue. Yeah. So generally, images are structured. You can see that this image as a grid form. Images are generally grid. Okay. So you can employ a deep neural network like this, or you can employ a convolutional neural network. Okay, because the structure being uh, structured is being uniform. Okay. So when it comes to text or speech, you can see that it is a sequential more than a structured like a grid. It is sequential, and you have sequential algorithms. So here you have RNNs. Okay. So you have RNNs. Just a minute. Yeah, you have RNNs. Recurrent neural networks. Okay, which nowadays you know that you talk about LSTM, and you can talk about say GRU, gated recurrent units. Okay, so these are examples of RNN, and now we have so many of other advantages, other innovations that have come out. Attention networks, self and cross attention networks. So which form the foundation of your transformer models. Okay, so they actually these type of networks are especially useful in case of text and speech processing. So where the data is sequential. Okay, so likewise you can find here that this is an example of LSTM, long short memory. And here, this image, you can find that this is mostly a deep neural network. Okay, so it is mostly a deep neural network. Or what I can do is I can also have something called, I can have a convolutional network where I can have a filter so that I can take this filter across 9x9 filter, and I can move this filter across this image, and I can capture the features. Okay, so that is called CNN. Okay. So I can either use CNN or RNN. So they are examples of deep neural network models, okay, which can be used on structured data like images and text. But our position today is slightly different, because what we are dealing with is graph. Okay, and graphs are something which are different. Okay, for example, here you can find the different types of graphs. So you can see that how different neurons are connected. Okay, so how the neurons in a brain are connected. Okay, so that you can see you have a visual cortex, you have an auditory cortex, a olfactory cortex. So how the neurons in a cortex, how they behave. Okay, so this is a knowledge network. This is an information network. This is how molecules in a protein are connected. Okay, how genes are connected. Okay, this is how emails are sent, communication is sent. So based on, and this is of course a social network with friends and other things. So you can find so many graphs around us. So these graphs are not as structured as these. They are not as structured as this particular images. Okay, or speech. They are not structured. So here, what is that you have to find out? Okay, so here you have to find, you should have a different kind of technology that is called a deep neural network. Okay, so we're going to have a graph-based network. So we're going to have a graph-based network. So in a graph-based network, okay, so again we do the same thing. So what is that? For example, like what we do in a graph-based network? Say you have a node U. Okay, so this node U has to be represented in a embedding. You have to it's an embedding in a D space, in a D dimensional space. Okay, so this may be hundreds of nodes or thousands of nodes. You take a particular node, and how do you represent this in your D dimensional space? That's called embedding, graph node embedding. So how this embedding has to be done, has to be learned by a neural network. So a neural network has to learn this embedding and convert a representation for this node U. So how does it do? It takes the U node and sees how many degrees are there. It finds out who are their neighbors. Okay, and after finding who are the neighbors, it finds whether this node U, whether it is having a between a centrality or whether it is having a closer centrality, as I measured, as we did in the previous lecture. So based on different centrality measures, I can assign embedding for this node U. Okay, so the embedding for this node U will be different from the embedding for this particular node, say call this node as A. So because where strategically you are placed, that defines your embedding. Okay, so this is called graph neural network. Okay, GNN. Okay, so this is a new field. So rather than going for a CNN and RNN, which are specifically applicable to images and sequential data, graph neural networks are mostly deep neural networks that are applicable to graph structures. Okay, and you can see that the graph structure is not as structured as an image. Okay, so it's totally different. Okay, so like you can find, that you have a graph. Okay, and that graph is embedded. This graph is embedded. So some embedding is done, and this graph is embedded in a d-dimensional space. From this, you can create your own different layers. For example, I can have a activation functions, a ReLU function, or I can have some regularization, dropout, all those things I can do in different layers. And finally, I have a node embeddings. Okay, and based on this node embeddings, I can do different analysis. Okay, so that's what actually is all about deep learning in graphs. And here you can see that how this deep learning differs. For example, this is an image. So on image, I can do a very good CNN. But here, how do I do a CNN? So here, what I will do is I will take a node and I will, of course, the neighbors, only the neighbors I will take. So example, this. Okay. Or one half neighbors. Okay. Depending upon the complexity. Or you may take two half neighbors. Okay. So you can take one half neighbors of a given node and you can apply your convolution on that particular node. Okay, but here the convolution is very easy because it's structured format. So here I can have a 3x3 or a 4x4 convolutional filter, and I can move this filter on this image and I can extract features. But here such a easy way is not there. So what we have to do is we have to go for a graph-based convolution network. So wherein you have to take a node and you have to do the convolution of that node or the embedding of that node based on its neighbors, only the one half neighbors. So there is no fixed node ordering, okay, or no reference point in this case. Okay, so this is what makes learning in graphs little difficult. Okay, so all these things I have already told you. Okay, so like for example, there are other ways of they are doing it. Say for example, you have a network like this. You take the adjacency matrix, combine the adjacency matrix with the features could be anything. It could be degree or whatever it is. So features, just put them side by side, juxtaposition them just side by side, and you apply them to a dense network. This is how you can do. Okay, this is one way of doing it, but this is slightly difficult because actually the size of the matrix is very big when D becomes large. Okay, suppose I have a Facebook where I have million nodes. So in that case, your adjacency matrix becomes very, very large. Okay, so and it is actually sensitive to node ordering. So that's again another problem. Okay, so like you have a CNN on image is very simple, like here what I showed you, but the CNN on this is very difficult like this. Okay, so here what you have to do is you have to apply CNN to a particular node and its one half neighbors. So that's how we can, and that is not uniform across all the nodes. Okay, and now what we can do is so that's what I told you. So here you can see that you take node A. Node A I can embed. Okay, say I can find who are the neighbors of node A. Node A is neighbors of node A are B and D. Okay, so now neighbors of node A are B and D. I can take node B and node C and node E. So they are the neighbors of A. So I can take them. This one I can take. This one I take. I can take B, D, B, C, and D are E. B, C, E. So not E. Sorry. B, C, and D are neighbors. So B, C, and D are neighbors. Now what you do is to embed A, I have to take B, and B, you see that B is connected to A and C. B is connected to A and C. So the embedding of B I take and so I take, see, I can just take the one hop neighbors. Okay. So I'm just taking one hop neighbors of every node, and you can see that this, I will call it as a computational graph. This is called a computational graph. Call it a computational graph. Okay. And so that's the reason why graph neural networks are very easy to work in case of computational graphs. Like you can have a tensor flow. So where basically it is a computational graph. Okay. So you can just see here and say how this target node A is actually good. Okay. So it goes through different layers. Okay. And based on that, I can have my hidden layers. So this is the hidden layer. Okay. And my number of nodes, neighbors of V. Okay. Take a node V, number of neighbors, the hidden layer. Okay. Sum on all, every node in the, which is present in the neighbor of n of V is the neighbor. For every node in the neighbor of V, I compute the sum. Okay. And what I do, I subject it to an activation function. So this activation function can be a sigmoid, or it can be a ReLU, or whatever it is. So it applies to this the entire, and this is weight matrix. So, and I find the next layer. So this is from the hidden layer 1. How do I go to the hidden layer I? From hidden layer I to hidden layer I plus 1 I. So this is how actually it is. Okay. And what you can do is you can always have a sharing of parameters. For example, here you can see that at this level, I can share parameters. For example, if we take node A, you can see node A takes node B and node D and node C. But when I take node B, the node A is again a neighbor. So that you can see that the parameter sharing can be done. So you can see that the parameter sharing can be done in each layer. In each layer, I can have very good of parameter sharing. Okay. And this results in very good, say, I have generated embedding for 3 nodes, but using these 3 nodes, I can create embeddings for other nodes, which are not trained. Okay. So, and for example, if I done for A, B, and C, then I can automatically learn for E and F. I can automatically learn E and F from this particular node. So that's the key benefit of this particular GNN. Okay. Okay. So now with this, I would like to end my presentation. And if there are any questions to answer, we can discuss.
Now it's time for participants to ask their queries and clarify any doubts with the resource person.
Hello, sir. Am I audible?
Yeah.
Sir, I have asked a question from the introduction part, whether this can be that network analysis can be applied for HR analytics, data analytics part.
Yeah, you can apply. See, I told you, wherever you have a structured network, okay. Say, for example, if you have a hierarchy, okay, or if you have any organization, they have a structured, so it is only just you have to map it to a graph structure. Okay. So you have to find what are the entities that map to a node, what are the entities that map to a role or a link between the nodes. Okay. So depending upon that and the role, for example, as I told you, example I gave you about say Instagram, when you take, you have to A follows B, B follows C, something like that. So you have a directed edge. But whereas if you take a Facebook, then A is a friend means B is also a friend. So in that case, there's an undirected edge between them. Okay. So based on the kind of entities that in your organization, based on the relationship between those entities, whether it is unidirectional or bidirectional, you can always cast it into a graph structure. Once you have a graph structure, then now there is a very good literature of works that are there without using deep neural networks. Without using deep neural networks, there are so many analytical methods that are available in graph structures to know about the what do you call the centrality of a node. To find the prominence of a node, we can have so many algorithms without deep learning. Also, you can find communities. You can also find communities in a network. That is also algorithms are available where you can find them without the help of deep neural networks. But with the advent of deep neural networks, now people have started applying deep neural networks to network analysis. Okay, so social network analysis.
Okay. Thank you, sir. Thank you for your explanation.
Yeah. Any more questions?
Participants, do you have any queries?
Sir, if nobody is asking, can I ask one more question?
Yeah, sure.
Sir, you have mentioned that in the small world problem, the maximum degree that we can have is 6. That's
Yeah.
the degree of separation. Is it universally proved and you
Yeah, it is
got
universally
like
true for any network. Actually, they say that any large network, you
okay,
may find that it is very. You may see that the two nodes are very distant. But
okay,
actually, when you just go through this experiment was performed by Millikan. Actually, it's called Millikan's small world problem. It was performed long back. So it's just like passing, they wanted to send a letter. For example, one person wants to send a letter. For example, I want to send a letter to the president of US. Okay. I'm not going to directly address him and put it in the post box. Okay.
yeah,
What
yeah,
I'm going to do is
absolutely.
I'm going to give it to my friend, whom I know very
Uh,
well, my first half of friends, and they will in turn pass that letter to the best half of
I
their
got it.
friends,
I
like
got
that.
it.
So in that case, they found that the average degrees of separation was only 6, not more than that.
Oh,
Some may
okay.
take more. Say some may take the 10, some may take 20, but the average,
Oh,
the average
oh, this
degree
is
of
average.
separation
This
was
is average.
6. Yeah, 6. Yeah.
Okay,
So that's
okay.
why it's called
Thank you.
the 6 degrees of separation. So that's the reason in internet also, even though you have so many vast number of hosts connected, okay, but the maximum number of separations will be 6 only. So average
Okay,
number of separations will be 6 only. You can have 6 routers or
okay,
6 hubs between any two hosts. Okay, so that's applicable to any network. If you take a biological network, also if you take enzymes, how proteins interact, there also the same principle applies.
okay. Thank you, sir. Thank you so much for your explanation.
Pooja, you start, ma.
Thank you so much, sir, for your valuable and informative session.
Thank you so much. I once again thank the organizers for having given me an opportunity to interact with the faculty in this FDP program. Thank you so much.
Thank you, sir. Thank you so much, sir.
The link will be posted in the chat box. Participants, please take a moment to provide your valuable feedback. And participants can take a short break for 15 minutes. The next session will begin after the break.
பிளாக் ஸ்லேட் பேசலாம் ஒரு புக் தாங்க வச்சுத்தரேன் முன்னாடி வேட்டைக்கு வர வேண்டிய
We extend a warm welcome to everyone joining us for the next session. It's with great pleasure we extend a warm welcome to a person whose impressive academic background and extensive professional experience bring a wealth of knowledge and expertise to our community. His journey as a software engineer at Patni Computer Systems, coupled with over 18 years of teaching experience as a lecturer and assistant professor, predominantly in Nagpur, India, and more recently in Oman since 2017, underscores a versatile expertise in both industry and academia. Notably, his contributions as a program coordinator for MTech CSC and his role in establishing the master's program at RCOEM Nagpur reflected the leadership and dedication to academic program development. Furthermore, his proactive initiatives as an industry academia coordinator at RCOEM Nagpur, including the establishment of internship programs and fostering collaborations with industry giants like Infosys, exemplify his commitment to enhancing student experiences and bridging the gap between academia and industry. His research interest in data science, data mining, and social network analysis align perfectly with our institution's focus on cutting edge technologies and innovation. Now, let's welcome Mr. Mangesh R. Vanjari, Professor IT Department, University of Technology and Applied Sciences, IPRI, Sultanate of Oman, to take over the session on the topic self-organized criticality based analysis of opinion dynamics in X Twitter. Over to you, sir.
Thank you so much, Dr. Pooja, for introducing me. And very good morning to one and all present here. Thank you so much for inviting me for this talk. I hope I am clearly audible to everyone.
Yes, sir.
Yes, sir.
Okay, thank you so much, ma'am. So thank you so much for inviting me to this session, and it's a great pleasure to speak to the people back in India and at various places about what you do and what are the things happening around. I have been listening to the talk of Dr. Thangarajan, and it was really very dense mathematically, and it has actually highlighted many things which we do in social network analysis. So I hope I will be of some impact when I am talking here. Basically, my talk is not about telling what we do, but I would like to invite many people to work on the social network analysis, because this field is the one which is going to rule further. Whenever there will be any social analysis or opinion analysis or any kind of social studies will be made, mostly the social media will be the place where we will have to find out the data. So let me first share my presentation. I hope you can see my presentation. Is it visible?
No, sir.
No, sir.
No, sir, it is not visible.
Just a minute.
Yeah, visible.
Is it visible now?
Yes, sir.
Yes, sir.
Okay, thank you so much for confirming. So basically, the idea and the reason of giving this talk here to the research community from various places and I hope some students are also joining, maybe some from graduate or undergraduate students. So I hope I will be of some sense to all of you, and I will be able to just create an interest between many of you to join the social network analysis community. So my topic is basically a little bit of interdisciplinary, which basically talks about self-organized criticality. But before that, I will try to create some basically this talk will be divided into three parts, where I will discuss briefly about the complex systems, right? And then I will talk about little bit of self-organization. Once I give this brief introduction of these two topics, I will be talking about
Hello, sir.
Yes, ma'am.
Hello, sir.
Yes, yes, please.
Your screen is not visible, sir.
Okay, let me check. Okay, what I will. I will share entire screen, then hopefully.
Somebody, Ganesh.
Is it visible now?
No, sir.
It will take a little bit of time. Wait.
Yes, sir. Now visible.
Now it is visible, sir.
Right now.
Yes, fine.
Yes, sir. Fine.
Right. So, sorry for that little disturbance.
Yes, sir. It is visible.
My topic will be divided into three parts. Basically, first I will talk about the background of complex systems. I will talk about what is self-organization and what is self-organized criticality. And then I will just try to create the analogy between these concepts and the social networks. And then I will discuss some of our findings. Okay. So that part I will not concentrate more upon, because my idea is to create interest between people to come and join this community of social network analysis. And still I will discuss our work, what we have been doing. So let us start with understanding the complex systems. So I can understand that every one of the persons here understand this thing. So if we look at a car, it is a complete system. But car is also an example of a complex system. So when you want to explore how car works, then you will have to divide each and every part of the car to understand the complete assembly, how it works, right? And then if you want to analyze if it has any problem, so if you want to give the car for fixing for a particular problem and you do not know the problem, the person who is fixing the car will have to look into each and every part where the problem is, right? So this is one analogy I can give you. So what is a complex system? So complex system, there cannot be a specific definition or any formal definition. Those who are from mathematics background, they know it well. But I will try to just give you a simple understanding that in a complex system, if you look at the example of the car we have seen just now, there are many different parts and they are heterogeneous parts. They are not same. Now they have intercommunication and relationships to perform particular tasks they have been assigned to. So this is something is a simplest form of any complex system. So if you mathematically try to put it in the pictorial sense, you can simply look at this, that there is a set of multiple heterogeneous elements which are put together. Okay. Now if you look at something like a naturally occurring pile of stone or anything where the nature of each element is similar to each other, then it also becomes a kind of system where each element of the system exert some pressure or force on the other element, and they actually arrange themselves in some sort of organization. Now, this organization, if you want to look at, and all of the elements of that system are similar in nature, then mostly if you look at, you can simply add, right? And then add their characteristics, and you can try to understand the complete system. So if all the elements are of similar characteristics, and if you want to create a system using similar characteristics, it can be relatively easy and simple to do this. Okay. Now, when you look at the complex system, and when you look at the people as a part of a system, now when you have different people who are related to each other, or who are trying to be a part of a system, then you cannot directly deduce anything based on the personal nature of the people, that in what particular way the system is going to perform, right? Now, if I take two elements of any social system, and if they come together, it is not always the subtraction, or it is not always the addition, right? So it can be something else also. So what kind of relationships can go, right? And how the elements properties can change when they form a system is something which is very
என்ன ஆன் வந்து தெரியலையே மேபி
sorry, anyone is trying to ask any question? Okay, fine. Now, see that example of a complex system. You can just see the illustrations, and you can understand that the complex system is actually a collection of multiple heterogeneous elements having interrelationship, some sort of interrelationship, which actually comes out and emerge as a single system, right? Now, this is just a part. I am not going into the deep mathematics of that, and I am not going to explore the complete complex system part of mathematics. Those who have been working in the complex systems, or at least having some background of mathematics, and have worked into some multivariate domain, they must be knowing about the complex systems, right? Now, if you look at the discussion I have made so far, or I just had for a moment, first thing we have to understand that any social network, now there are many examples of social networks, and they have actually boomed just after the web 3.0 has come into existence, right? So you have Instagram, you have Twitter, you have other social networks, where we actually have the kind of specialized groups like LinkedIn and other stuff. So first thing you have to understand is complex system is something where multiple heterogeneous elements will have some relationships, and they form as a they emerge as a complete cohesive unit, but without any central control. This is very important. So we can understand that if there is no centralized control on the elements of the system, and they have the interlinks and relationship between them, and they interchange some sort of exchanges, then there is something we can always say that this particular system can be modeled as a complex system. So if you look at any social network, every individual is a separate entity in the social network, and we do not know how that person is going to behave in what situation. So every person is different, so heterogeneous elements are already there. we are connected with links. The way, if you can look at the social network graph in the previous session, you might have seen many graphs, previous session of Dr. Thangarajan. So there were many social network graphs he has shown as an examples. So you already know that all these elements are connected with some sort of links, and they are communicating with each other without any central control, right? So we can say social network is a complex system. Then it is non-linear, because there is no single dimension. There are multiple dimensions, and it is non-linear system. It is interdependent, so multiple elements are dependent on each other for their opinions, for communications, for trends, or many different things. And heterogeneous nodes exist in the network without a central control. So these things actually define our social network as a complex system. So I hope I make sense, and that actually convince you all that social network can be modeled as a complex system. So once it is there, there is a unique property of any complex system which is called self-organization. So we actually, knowingly or unknowingly, if you use Twitter, you use Facebook, or if you use any other social network, we can always say that we actually get modeled, or we actually get divided into some sort of things where we can see disagreements, where we can see some polarization, we can have like-minded views, and we eventually become part of that group. So this kind of self-organization will also be there. Now, second topic I need to talk about is what is self-organized criticality. Now, this is a very interesting phenomena, and most of the people from computer science background may not know this. So I would just like to spend some moment on this, explaining this particular topic, right? So this was actually coined by Per Bach in 1987 in his very famous paper, and they have also published one very good book on that, how nature works. So Bach, Tang, and Wiesenfeld actually have given a very good explanation of many different models of self-organized criticality. Okay, and their experiment is actually called as BTW experiment, based on their first names, or based on first letters of their names. So typically, what this idea is, this is actually from the physics, and how I happened to get into this field was because there was one professor, he is now retired, in my previous institution at Ramdeva College of Engineering in Nagpur. So he was, along with another collaborators, he was working on this field, and he was looking for somebody to help them in programming the model. So he approached me. By that time I just joined that institution, and somehow we met in some connections, and then he approached me to help him with the programming part of that. So I helped him program, and then I have seen what they are doing. So they were talking about this part of physics, which says that all the physical systems in the world follow self-organization. Means they will be in equilibrium most of the times, and there will be some sort of force exerted by every other element on its neighbor. Okay, so if you see, every single element is giving you the inputs, right? So if you are in a social network, your neighbors will be giving some kind of messages, or they will publish some of their messages, or they will send you messages, and you will get notifications. Now, as soon as you get these notifications, what happens is, we actually also get influenced by that point of view. Now, there can be three types of reactions from every single user. So first reaction you can always think is that you are going to be neutral about that particular phenomena or that particular message, or you can be reacting negatively or you can be reacting positively. So these are the three possible sentiments you can have about. Sorry. Okay. So there are three possible phenomena for this particular event. So anybody sends an event who is from your own network, you get the notification or you get to see that event or message, and based on that message you can form your opinion. Either you can be neutral, you can be positive towards that opinion, or you can be negative to that opinion, right? So now what my idea was that this happens with the physical system, then why can't we go and check whether this happens in the social network or not? And that way I actually came into this point. So you can see here the network is always stable in the beginning, and then as you get the messages and you start forming your opinion about particular element, so these normal incidences will happen and then your system will actually get affected. But as these exchanges are getting too many, and your if similar particular topic is actually too hot and you are uh, involved too much into that topic, then your opinion will actually get formed, and eventually many elements from your network or on from that region of interest will be sending lot of messages to that. So this basically says that in a physical system this happens. What I tried to make the analogy is that this can happen in the social network also. So this particular illustration will give you some mathematical representation of how I can model the system. So this is just a sand pile model where you are putting some grains from the top. Suppose I go here. So this is a sand pile model. You are continuously pouring in some elements of the sand, and what will happen, they are going to exert pressure on the part or on the element when they are actually going hitting, and that element in turn will change its energy, and all such grains one after the other will do this. Now when you change this energy, after some time it will reach to the place where all the elements of that grain pile or sand pile will be disturbed, and after some time everything will actually collapse. So what is the idea is, when you are exerted with some pressures from your neighbors, you will be disturbed momentarily locally, and you will forward that. So either you will express your uh, positive sentiments or negative sentiments, and you will also post. When you post, your neighbors will also post as a reaction to that, and when this chain reaction actually grows and everybody in your network posts about it, then there will be some point which is a critical point, means everybody will release their energy at that point and again come back to the equilibrium, which was the state before this event happened. So similarly, if you want to model it as a grid network, you can simply see here. This is not my slide, but this is the example in the Purbach book, or how people have modeled in the physics, right? So see this. These are the initial energies. Assume that these are the initial energies of each particular sand element in that pile. So assume our critical stage is everybody has 5 energy. So take 1 unit as the energy unit, and maximum can be 5. So as soon as any elements become 5, he will exert the pressure on its neighbors. So neighbors will be only top and bottom and left and right. They are in direct contact. So it will exert the pressure on that and it will try to release. So here if the sand grain falls on 2 by 3, 2 comma 3, that is this 4, okay, second row, third element. So if it falls on 4, means the energy will increase by 1. So as soon as energy gets increased by 1, its energy will be 5. As soon as it becomes 5, it has become unstable. Like we also get tempted to write our opinion. So this element will exert its will express its opinion or exerts the energy on its neighbor and releases its energy. So it will transfer 4 energy units to the 4 neighbors. In turn, the 4 neighbors will receive one energy unit and their energy will grow by 1. And this point or this region of interest, or say you can say the point of initiation, that particular element has exerted 4 units and it becomes stable. Now in turn, 2 different elements have become unstable. Now they will release their energy to their neighbors and then they will become 1 but in turn another neighbor will become 5 and he will exert the pressure. So this is called avalanche effect in the physics. So once some element becomes unstable and in turn it exerts pressures or energy release on the neighbors energies will also get changed, and in turn their energies will also grow and be above some uh, threshold, and then they will also exert. And similarly, if these perturbations go to all the elements of the system, then there will be an avalanche effect. So my idea was to take this and model it into the social network. Can we do this? Right? So there are 2 different models I was interested to know implement into the social network. So first one is the earthquake model. This is also a very famous model where tectonic plates are always there, and the elements will be there on those plates and they will be exerting pressures continuously. Now when this goes to a certain limit, means all the elements actually go to a critical energy level and they immediately will release all the energy they have, and then earthquake comes. So this happens for momentarily, and all the elements into the system or all the points will actually settle down to a equilibrium energy after that. So this is what happens. We can see many such phenomena in social networks, that there is some issue related to movie or some political statement or some social event or some controversy. So lot of elements in that region of interest will get hyperactive, and they will express their opinions either in the positive or negative sentiment, and the things will actually start vibrating, and the propagation will go to the larger extent, and there will be some agitations happen or something will happen, and eventually everything will be dying down. Now what our idea is to understand that the self organization is uh, the property of any complex system. Then there is something called self organized criticality. So every single neighbor tries to exert pressure on the neighbor or connected nodes, and in turn those nodes will also gain or lose energy, and then they will try to pass it on to propagate that energy, and things will change. So here, just to summarize what we have done in the complex systems, what we understood from the complex systems and what we understood from the social self-organized criticality, to summarize it, there are 3 things we have to understand. First is self-organization, that all the elements are different, heterogeneous, and they are into the non-equilibrium system. Okay, and they have actually created some structure and patterns so that self-organization of that particular region of interest in the social network has been created. Okay, now there is no control or manipulation by any external agent, but these elements of the system will actually have some more or less effect. So there can be influencers, there can be just receptors or follower-followee network. That's it. Then there is a critical behavior of the system. Critical behavior says that at a particular moment of time, most of the elements of your system or your self-organized region of interest, ROI, most of the elements are active and something is trending or something is actually boiling. Okay. And we can set some threshold, and if it goes beyond that, we can say that it is actually in the critical state. And there is complexity, that there is a consistent interaction between the different elements, and that will have exchange of forces or information within themselves, right? So I hope I make sense, and I have given you the enough background of how I came into this, how I have tried to establish the analogies between the physical systems and the social network analysis, right? Now this is just to give you the same thing what I was talking about, that is the look and feel of that. So there are many different people. Heterogeneity in the social networks is inbuilt. Okay, there is no central control. Now neighbors will influence each other, because every single messages posted into the network will be notified to the neighbors or the people who are following closely to that person. Okay. Now once you receive anything or any news about anything, so point of origin will be there, and from that point of origin, if that message has the capacity to create the perturbations across the system, then they will create, if that message has the content which can do this, right? But before covering or before influencing the complete region of interest, it will have some local perturbations, and these will always be there. Some issues will be there which are locally active. Those issues will get die down eventually. So what happens now, what we are trying to do is, we try to understand that every individual person has his own opinion about a particular thing, right? Now when we have our own opinion, which is not influenced by anyone, before we get into any such discussions, so these opinions are your own opinions, right? But now when somebody from your network or from your neighborhood posts something about that topic of which your opinion is there, about which you have your own opinion, then when you look at the content of the message, your opinions start changing. So what we are trying to model is, we are not trying to model the energies, but we are trying to model the opinions. So let us assume that if I look at this model, I am going to look at what is your initial opinion when you look at the first matrix here, or first grid. So initial opinions of the users about a particular topic will be initialized. Now when a user will send any message about that topic, your opinion will change based on how you react after that. So what was your initial opinion, that was already initialized, and now when somebody is posting any message about it and it has actually reached to you, your opinion may change. So that opinion you have expressed is different than the opinion you have expressed before, right? So it means that due to the message received from user A, you have changed your opinion about some point, uh, uh, some topic, say, and that opinion has changed by del t, some delta. Yeah. Oh. So are you not able to see my files? Okay, sorry. Sorry, I am not able to share now. Okay, now I can. Are you able to see now?
No, sir. Yes, sir. Now visible.
Now it's visible. Okay,
Yes.
so how many slides you have not seen? I don't know. This slide only, right?
Before.
This you were seeing.
Yes, sir. Yes, sir. Yes,
Okay,
yes.
then we have not missed anything. Okay, so see, now your opinion will change by the influence of your neighbors or the influencers you follow. Now, when your opinion changes with time, you will be polarized with some opinion, right? So there will be agreements and disagreements between different people, and accordingly your polarized groups will be formed. So you can also observe this, that in many social networks, if you are part of, if you follow a particular opinion, all the notifications you get by the system automatically will be based on your likings. Okay, there will be very few elements which you do not like and they are also pushed to you, but most of the times the polarized things will be there and you will be put into a particular group, and you will get polarized based on the influences you are under in any social network, right? So what our idea was, initially we have started with the earthquake model, and then we tried to understand these opinions, right? So opinions, initially we have considered the d-dimensional cubic lattice of size n, right? And then we have actually considered it as a graph, and we have created a regular graph with a cubical structure, and instead of having a neighbor of 4 neighbors, we have considered 8 neighbors to be influenced, right? But when we have seen that these energies we were able to propagate, and we were able to run our probabilistic models for seeing how opinions do change, it was getting very difficult to model logically our graph into the lattice structure, because it's very common to have more than 500 neighbors, or the network of 500 or more neighbors. So when we have downloaded the data sets, we have we have seen the follower and following network, then choosing the elements from that big graph to be put into our model, and then forming the cubic lattice was very difficult task to do. But we have run some probabilistic models on that, right? So here what we have done is, we have actually tried to check the complete energy of the system based on the sentiments, and when it actually grows above the certain critical energy point, that whatever thresholds we have put above those thresholds, if the energy of the complete system goes, then all of the system will release the energy at once, and this is the propagation or change equation we have considered. Okay, that all the elements, that is the elements of all the edges, will try to become zero, they will try to change, and their neighbors will actually gain something from that. Okay, so this is how we have modeled the system. Then we realized that we are not able to capture the characteristics of the network, because we were selecting the nodes which were not relevant in many of the cases, right? and it was very difficult to select the subgraph from the big network graph and form logically the lattice structure. So this is what means we have taken the subgraph, and then in the subgraph we have tried to create some sort of logical structure, but then we realized that we are not able to get the characteristics which we need. Then what we did is we have actually, so there are many people working on this area now. So one of the teams in IIT Kanpur under Professor Niloy Ganguly, and they have their own lab there which actually works on this area. Then there is one lab in set up by Dr. Abir Day. So they have been working on this topic since long, but they have not considered social network analysis or self-organized criticality. So when I spoke to them, they have actually shared their data sets with me. So they have their own model of studying the opinion dynamics in the system. So what we are trying to do is we are trying to combine what they do and our approach, and we are trying to find out the approach which we can go with. So at this point of time, what we are doing is, some of the assumptions here are the assumptions from the same work of Dr. Abirde and his team. So these two data sets informations we are now working on. So follower following network we are taking. So this is the Twitter data set only. So earlier they were working in the MATLAB. The MATLAB was their basic programming model. Now they have also shifted to Python, and I basically work with Python. So the record of there are two things: one, network showing who is connected to whom, right? And we denote it with a graph, a typical graph with vertices and edges. So record of all the messages posted by users within a specific time frame. Now what we have done is we have taken the data sets. I will just show you the data set, how it looks like. So when you download the data set from the Twitter, I have just taken some of the elements where this is the text of the tweet, this is the user screen name, this is username, and this is location, right? So I have extracted only few parameters to show you. So this is not the data set I am working on, but how we get the data set from the Twitter, that is I am trying to explore. I was told to conduct a practical session on how to get the data sets, but looking at the forum right now, more than 200 people joining and then doing programming here and then explaining may not have made sense. So I just dropped that idea, and I just thought of showing you this. Those who have not worked, or who have not scraped data from the web before or from the Twitter. Earlier, Twitter was giving free account to the academicians for with a lot of abilities, but since Mr. Elon Musk has taken over, he has actually made it paid. So even my account is now paid. So if you want to get data from Twitter based on your own problem statement, what kind of relevant data will be for you? So there are many different ways you can get the data from Twitter. So one of the libraries which you can use is this Tweepy. If you can go to Tweepy, Tweepy is one of the most popularly used library for getting data. So if I explain how to get data, I will be using these examples which are there in the Tweepy documentation mostly. So I am just asking you to go there and just check how to get data from the Twitter, and try searching. Many examples are there, or there are many forums where people talk about how to get data even after the changes. So now currently, if you look at even the basic account, they are giving for $100 per month. So if you are not in if you do not need any specific data, then no need to pay. But if you want to get the specific data, then at least you can pay for a month and then you will get some access, but there will still be limit. If you want say unlimited access to Twitter API, then you will have to buy it for around $5,000 per month. So that is too much money for academicians. So I would suggest you to go with the data sets which are available, or go with the just ask the people who have already published, work on the similar lines, and just ask them the data set. They will be happily doing it, but you will have to abide by the rules and contract terms they had while they got data, right? So that's the thing. But if you want to yourself download the data, then you will have to make a Twitter developer account. They will give you access tokens and the access keys, which you have to put whenever you create application. And then when you identify yourself with your keys to the Twitter API, Twitter API know what your account is, what your identity is, and they can also track how many tweets you are taking, what are the elements you are looking for, and you have to sign certain agreements with them. Means you have to just look at answer some of the questions. So that is just an idea how you can get the data from Twitter, right? So coming back to what we have been doing, so I have two sources in my data set. Basically, it's a network showing who is connected to whom. So this data set, I am using the same data set which Dr. Nilay Ganguly's and Dr. Abhirdesh's team has actually used, because they have very good applications and I have to compare our work with them as well. So a network showing who is connected to whom, and then record of all messages posted by users within a specific time frame. So this is an open interval. So each message is summarized using three things. Okay, the user who have posted it, that is UI, the opinion value of the message, that is SI. Now earlier, if you want to create any commercial grade application for sentiment analysis, then you had to really spend minimum 5 to 6 months to create a good application, because there was a lot of things involved, natural language processing, then finding out the different things, and then getting the sentiment score. So this data set has actually created the sentiment scores from the data by filtering out how many and which particular elements of the tweet should be kept in, and which user should be selected. So the data set actually has minimum 200 followers and above. Right now, this sentiment is the original sentiment we have, but every time you send a message, that is a message event, that message event will have sentiment score associated with that. So data set was downloaded and sentiment score was calculated based on the standard practices which are published already and which are used. So the timestamp of the post is also considered, at what time it is, because this is a temporal analysis, because with time how your opinion changes. So what we are trying to find out is, you were having some opinion, now there is some trend going on. Within that trend, when you are posting on the same topic, after you read the messages of the people you follow or you get notification about, and then after that how it changes. So what we are trying to find is, for a particular group of people in that region of interest on a particular topic, how the opinion will get converged, whether it will converge or there will be disagreements or not. So that is the basic Twitter dynamic we are talking about, opinion dynamics. So your opinion was having some value, and so was the other elements into your network. With time, how your opinion has changed, and whether that particular group of people have converged on a particular opinion or not, right? So I hope I make it clear what we are doing now. So U of t is the collection of all the messages that user has sent, okay, up to a certain time t, okay, and this t is less than our time interval we are considering. Now I can mathematically represent it as u of t such that every message event ei, which has three components, right? What is the user name, what is the sentiment, and at what time it was put. So we collect all such messages which are posted before the time t, the time we are taking into consideration, right? Now we will also consider the history of messages, right, for all the users in the network. Okay, so this is also similar. It is the history of all the message events where every UI we are taking for a particular user, and then again the condition is the point of time or instance of time, all the messages should be before that. So it is the collection of all the messages with some sentiment mi posted by a particular user, not all the users, which belongs to our vertices until the time. Sorry. So for a particular user, the sentiment is mi, and for all the users we considered sentiment si. So si and mi domain is taken to be the same, right? So for modeling the message dynamics, what we have done is we represent message times by set of counting process. So we have denoted one counting process and taken some vector n on t, in which uth entry in that counting process will be nu of t, which belongs to this set, which counts the number of messages user u has posted until that time, right? And then we try to find out what is the message rate. So if message rate has grown, we already know that the thing is the topic is already in trending, right? So if you can just see this explanation down, you will always know what is the message count or rate of change of message count, right? So basically this rate of change is actually a temporal process, and it has changed over the time, and when it has changed over the time, it has impact of the history. That is the idea. So these results I have not published yet, so I am not giving you the details of these results, but I am giving you how our results are actually coming up. So on the left hand side you can see this is the mean square error with the corresponding models we already had. Okay, so we have implemented these models on the same data set, and as we have not taken many samples to plot this, the curves are not very smooth, but you can see this blue line is our line, how it performs on the mean square error. So it performs better on the classical degrowth model and ASLM model, which many people use for opinion dynamics, right? And then how convergence happens, that is the model. So in our data set, basically the convergence happens, but there are I have around 20 data sets, which some of them do not converge, but I have actually put it on only that data set where we have the convergence of the opinion, right? So my idea is what I just wanted to make clear. I'll just conclude in 2 minutes. My idea was to have the mathematical or logical model to represent social network. Okay, so if our model is not very good, I cannot say it actually fits perfectly well, because we are trying to model things which exist in the physical system, and it has proved very well by many physicists that it works in the physical system. So we are trying to implement it to the system where our elements are human. So you cannot model human very easily, right? Because you cannot predict how human will perform in a particular situation. So that is one thing. So the scope here is how can we improve this mathematical model to represent each node in uh, each node of interest, right? Then second problem which is open in this domain still is there are many approaches you can initialize the sentiment score of each user in the network about a particular. So when I have to initialize to the sentiments, so what we have done is we have taken the first message of each person who has posted. Okay, now not all of them have posted, so what we have done is we have put their sentiment score to be 0 about that topic. So that initialization approach is not very good, because I cannot say that every person in the node who has not posted about a particular topic into the network will have zero opinion about that. That's not true. So here also you have one more, this is open, you also have this area open to come up with the mechanisms to initialize how we can initialize the sentiment scores of the people about the opinion, initial opinions they have, right? Then third area is when we do the computation, we are actually collecting the historical data and we are doing the computation, right? Now due to the Twitter restrictions on how many tweets you can take, or even if you take the complete control, it's not very easy to analyze the real time things. So this area is still open. Not many studies are done on the real time data, but this is also a very good option. Now what our idea about this is, if we can predict the perturbations or avalanche when it is going to happen, and with that if we can predict the future event, even say 2-3 days, what is going to happen after 2-3 days, that also can help the governments or corresponding agencies to take the measures to avoid those kind of events if they are not in the interest of the society. So that is predictive analysis can also be done, but for that you have to have access to the real time data in the network. That area is still open, and there is no predictive analysis which is accurate. This can be applied to the stock exchanges and all, but I do not know how we can model that, because I have not worked into that particular area. I am more interested in knowing the people's opinions about a particular thing, right? Then efforts can be made to reduce polarization and disagreements. Now this is something which I think is a very good topic, because we can see people are splitting based on their opinions, and they are not very good in mixing with the people uh, who are not having aligned opinions. So we can see that there are polarized groups formed, and to have the harmonious society we can actually make some efforts on the platform sites itself, say like Twitter, Facebook or Instagram. The efforts can be made from the platforms people itself, that this polarization and disagreements can be reduced by some conscious efforts, right? And there are other possibilities which you can explore, which I cannot also talk about right now. Okay, so this is all about what I wanted to tell you. I hope I have given you enough idea that what kind of works we can do, but there are many possibilities. I have given you idea about what kind of work we are doing, but there are many possibilities, and I do hope some of you will be interested to work with us on this particular area to improve what we have done so far. Thank you so much for inviting me. If there are any questions, we can take them.
Hello, sir. Am I audible?
Yes, ma'am.
Sir, I'm Roslyn here. You said that if you are interested, we could join you in proceeding further with the work, right?
Yeah.
So how are we supposed to approach you, sir, in this regard? Like, if I want to be a part of the team, so how am I supposed to approach? And what is the roadmap for that?
Ma'am, I am actually collaborating remotely with many people across, and we do not have any such team here in our university because we are collaborating independently with each other, not under any MOU or anything. So, if you want to join, I will share some of our works, and we can take up any topic, and we can work collaboratively on that. That can be done.
Sure, sir. That's what I'm expecting. Even I'm not speaking on behalf of the organization.
Yes,
As
yes.
an individual, as a person who's interested, I want to ask you this. So, if it is like I want to, on an individual level, if I want to collaborate with you, I just have to mail you. Is that enough, or how to go
Yes,
about
yes,
it, sir?
it's enough, ma'am. It's enough. Thank you so much. Thank you so much. It's
Thank
enough.
you, sir. Thank you so much.
Okay, if there are no more questions, we can just take a leave.
Yes, sir. I think that's the end of it.
Okay. Thank you so much for having me here. Thank you so much to the organizations from the both the organizations, and I really appreciate your efforts to bring together people on this area. Thank you. Thank you so much.
Thank you, sir. Thank you so much.
Thank you so much, sir, for your valuable insights, and it helps us a lot for a deep understanding on the topic. Thank you so much, sir. At the conclusion of our day one session, we extend our sincere gratitude to the organizing team whose dedication and meticulous planning have made this event possible. We also want to express our heartfelt thanks to our esteemed resource persons for sharing their expertise and insights, which will deepen our understanding of deep learning in social media analytics. A special thanks goes to the distinguished faculties and researchers whose presence enriches this program with diverse perspectives and valuable contributions. Thank you, all participants, for being part of this exciting journey. Let's approach this week with enthusiasm and shared commitment to academic excellence and discovery. The next session starts by tomorrow at 10 a.m. Thank you all.
Thank you very much, Mr. Mangesh, and thank you very much, organizers. Thank you so much.